Hello, 7th graders. We continue to discuss the big Algebra 1 topic of linear equations and their graphs. I've written here what is known in the trade of K through 12 math. This is known as the standard form equation of a line. And we say two things about it. First of all, the A, B, and C are integers. We don't write an equation in this form typically with fractions for A, B, and C. We say that they will be integers. And we, excuse me, we also say that the A and the B cannot both be 0. If the A and the B were both 0, then you would have 0 plus 0 on the left, and the C would have to be 0, and that's a pretty trivial situation that we can't do much with. Now, the A could be 0 by itself. The B could be 0 by itself. And also, the C can be 0. We're going to see what implication that has if the C is 0. But the A and the B cannot both be 0. And the A, B, and C are integers. This is one form of the equation of a line known as the standard form. We're going to consider one other form. When we get to Algebra 1, there'll be at least one other. So for a total of at least 3 different variations, 3 different looks to the equation of a line, but we're going to focus on 2. And the second one we're going to look at, I have a little bit of a technical issue with this. Unfortunately, I'll have to explain. Y equals mx plus, and I write n here. Just about all of the textbooks and anything that you might see online, if they're going to write the equation in this form, with general letters here and here, you're usually going to see a B here. But in my opinion, that's a mistake, because that might lead people to believe that this B is the same as the B up here, but it isn't. The reason a B is used by the textbooks is, I think, because this is the second term, and you might then say, well, why not have y equals ax plus b? Well, for some historical reason, the letter m is used to stand for the slope of a line. In this video, we're not going to get into the concept of slope. I'm going to define slope, and it's a huge part of this topic, the slope of a line. We'll start by defining it, and then we'll look at various implications once we define the slope of a line. But for now, we can just say that this number here that is in front of the x is the slope of the line. This n over here, this number, this is something you can understand right now. This is the y-intercept of the line. You already know how to take the standard form equation of a line and find the x and y intercepts. That's a very simple thing. You should have mastered it by now. You can also find the x and y intercepts of a line from this equation. And the y-intercept is staring you right in the face. There's no work to do. It's that number right there, what I call the n and which other people call b. Because if you put a 0 in for x, put a 0 in for x, the y is going to be n, right? M times 0 is 0, plus n is n. So the y is n when the x is 0. Let me write that this way, 0, comma n. Okay? This point is on the y-axis. So that n is the y-intercept of the line. This form of the equation of a line is known as the slope-intercept form. It's almost always said that way, slope-intercept. What it really is slope y-intercept. And the reason that it's the y-intercept is obvious. You'll have to trust me for now about this m being the slope of the line. So this is the focus of this video. How do you go from the standard form to the slope-intercept form? And it's not very difficult. I like to say that it is a 2.5 step solution of an equation. 2.5 steps. You'll see why soon. Here we have the equation of a line in standard form, negative 3x plus 2y equals 6. We'd like to be able to transform that equation to come up with an equivalent equation where we have simply y equals. Having y equals is a nice situation for a variety of reasons, including something that is known as functions. Functions take up a huge part of high school math, and when you write the equation of a line this way with y equals something, the thing over here is the function. And this is not something you can appreciate right now. We may talk about functions a little bit, but just trust me for now. This is a very useful way to write the equation of a line, which might lead you to ask, well, why do we bother with the standard form? Well, the standard form sort of has its advantages as well. It's traditional, and we're just going to have to live with it. And actually, not all lines are captured this way, y equals something, because there is a whole class of lines that are in the form x equals a number. You already know about those. X equals a number. Those are vertical lines, and you literally cannot write a vertical line in the form y equals something, because its equation is x equals a number. See, there's no way to do it. So I guess that's at least one reason why the standard form is necessary. But this form is very useful. So we'd like to be able to go from this to this, and here's where the 2.5 steps come into play. Now just keep in mind, we're trying to isolate the y, get the y by itself. Everything that I'm going to do here, you've already done. Students get a little bit intimidated by this, because when we solve this equation for y, we're not going to get simply y equals a number, like y equals -3 or y equals 5. We're not going to get that, because this is not a horizontal line. You can have, when you're dealing with linear equations in the graphs, you can have y equals a number, but this is not one of those cases. There's going to be an x over here when we're finished, as well as other numbers. But rely on the approach that you've taken for many months now for solving equations. If we're trying to isolate the y, what's a logical thing to do first? How about adding 3x to each side? Right? If we add 3x to each side, we're getting closer to having the y by itself. So let me write plus 3x and plus 3x. Now, I hope you realize I chose to add 3x because now these two add to 0 and go away. We're going to have a 3x added to the 6 over here. I'm going to actually write that as 3x plus 6 rather than 6 plus 3x, because that's the way it's generally done when we get down here to the final result. So what we now have is 2y equals 3x plus 6. Okay? The next step, to isolate the y, you know what to do. Divide each side by 2, right? And you will have isolated the y. We indicate the division as we normally do in middle school with a fraction bar. What I've just done is to divide each side by 2. Now you know that these 2's cancel, isolating the y, right? So in a sense, we're done. We have isolated the y. We have y equals 3x plus 6 over 2. Here's where the half step comes in. I said it's a 2.5 step process. What we're now going to do is divide this 2 into each of these terms and rewrite it like this. 3 halves x plus 3. Okay? Now, I'm going to show you step by step why this thing here, 3x plus 6 over 2, is equivalent to 3 halves x plus 3. But my explanation is not something I don't think you're going to do out on paper. What you're simply going to do is realize that this 2 has to be divided into each of these terms. Well, how do you divide 2 into 3x? So what's 3x over 2? 3x divided by 2. We're going to see that that's 3 halves x plus 6 divided by 2, or 3. Okay, Well, here are the steps. Do it this way. Think of this fraction that we ended up with, 3x plus 6 over 2. Imagine that it's two fractions added together with a denominator of 2. We're sort of breaking apart an addition, right? Well, this is clearly 3. Here's the plus 3. So now we've got 3x over 2. Now, that is the same as 3 halves times x. And here's why. The x can be thought of as x over 1, right? 3 over 2 times x over 1. If you take 3 over 2 times x over 1, you'll have 3x over 2, right? 3 times x and 2 times 1. But what's x over 1? It's x, right? So 3 halves times x over 1 is the same as 3 halves times x, which is what I wrote earlier. Okay? So 3 halves times x, y equals, after doing the two steps, we got y equals 3x plus 6 over 2. And then we can go from that to y equals 3x over 2 plus 6 over 2. And finally to 3 halves x plus 3. Now, this 3 here is the y-intercept of the line. This line goes through the y-axis at 3, because when x is 0, the y will be 3. The point 0, 3 is on the y-axis. That's why this is called slope-intercept. It's really slope y-intercept. This is the y-intercept, positive 3. And the slope of this line is 3 halves. It wasn't immediately obvious when you looked up here. You can do it mentally after a while in a few seconds, but when you look at this version of the equation, there's the slope staring you right in the face. Now, I understand we haven't defined slope yet. You don't really know what it is, but it's a number. I will start by saying this about slope. Every non-vertical line has a number associated with it that we call its slope. And then we will go on to define slope. I want to repeat that. Every non-vertical line has a number associated with it that we call its slope. We then define the slope and work with it, and it becomes a big part of our work in this area. Notice how I started that statement. Every non-vertical line has a number associated with it. Vertical lines don't have slopes, and we'll see why when we get to that topic. But this is not a vertical line. This line, whether you write it in this form or this form, this line has a slope of positive 3 halves. I think I've said this to you before. This might be a good time to repeat it. When we're working in this area, you should have another device or another tab on your computer where you can go to desmos.com, desmos.com, and then you can type in equations and see their graphs. It's a beautiful piece of technology. It's essentially what we had years ago, before iPads, before people were on the internet all the time. We had what are called graphing calculators. Well, desmos.com is a free online website where it's essentially a graphing calculator. And if you type in negative 3x plus 2y equals 6, you'll see the line that is the graph of this equation. And just for fun, below it, on the next line, you can enter several equations at once in Desmos. Type in y equals 3 halves x plus 3. If you type these two equations in accurately, type them in accurately, you'll see something cool. The two lines will be right on top of each other. They're really not two lines. They're not two different lines. They're the same line. The reason that this equation and this equation have the same line as their graph is because they're equivalent. I went from this equation to this equation through acceptable logical steps of getting an equivalent equation. Equivalent equations have the same graphs. Okay? So, we're on our way to understanding how to go from the standard form equation of a line to what is known as the slope-intercept form, where we have y isolated. And let's look at another example. 5x minus 2y equals 3. This is the standard form equation of a line where a is 5. And what's the b? Is it 2? No, the b is negative 2. And the c is 3. Let's rewrite this in what is known as slope-intercept form. In other words, let's solve this equation for y. It's going to be very useful going forward. We're going to like dealing with that equation maybe more than this one. You got to be skilled at using both of them. You got to be comfortable with using both of them, because that's how this topic in Algebra 1 is taught. 2.5 steps. We're trying to isolate the y. Our goal is to get y equals something. Again, it's not going to be y equals a number, because this is not a horizontal line. But we're going to, and so there's going to be an x over here along with other numbers. Subtract 5x from each side. We're trying to isolate the y, so we don't want that 5x on the same side as the y, so subtract 5x from each side. We're doing the same thing to each side of the equation, so whatever we get is going to be equivalent. These add to 0 and leave us with this. Here's a common mistake. You're not left with 2y on the left, you're left with negative 2y. Right? Negative 2y. And then notice what I did on the right side. Once again, I put the x term first. I could have written 3 minus 5x over here, but it's customary to put the x term first. So the negative 5x, and then this is positive 3 plus 3. One more step, and then sort of the half step. The one more full step to do to isolate this y is to do what? How do you get that y by itself? Divide each side by negative 2. Divide by negative 2. Divide by negative 2. So we have accomplished our goal in a sense. We have isolated the y. Y is equal to negative 5x plus 3 over negative 2. But once again, we're going to break that fraction apart, pretend that it was two fractions that had been added together. Think of it as negative 5x over negative 2 plus 3 over negative 2. Okay? Take a look at what I just wrote here. Ask yourself, what would I get if I added these two fractions? Well, you have a common denominator of negative 2, right? And you would, the numerator would be negative 5x plus 3. Negative 5x plus 3 over negative 2. It's like an addition backwards. Now let's look at this first. What's 3 over negative 2? Well, that's negative 3/2. Positive over negative is negative. So the y-intercept of this line is negative 3/2. That's what this number over here is. It's the y-intercept. And now we have this term, negative 5x over negative 2. First thing to say is that's positive, right? Negative over negative is positive. This would be equivalent to 5x over 2. Negative 5 over negative 2 is the same as 5 over 2. Negative 5x over negative 2 would be the same as 5x over 2. Now what about that 5x over 2? Remember what we did last time? That could be thought of as 5 over 2, right? 5 over 2 times x over 1. 5 over 2 times x over 1 would be 5x over 2, which is equivalent to this. But x over 1 is x. So this becomes 5/2 x. This is the so-called slope-intercept form of the equation of a line, where 5/2 is the slope of the line and negative 3/2 is the y-intercept. This equation is equivalent to this one. So once again, if you type this into Desmos and then on the next line type this, you'll see that the two graphs coincide point for point. They are in fact the same line because the equations are equivalent. One thing that just occurred to me, in both of these examples that we did, I believe the slope came out to be a positive number, but the slope can also be negative. This number here could be a negative number. So I think there's maybe one last thing to do, and that is the general case. Let's look at a general case. Can we solve ax plus by equals c for y? This is the general form of the standard form equation of a line. Well, it's still 2.5 steps. That doesn't change. And the first step is to subtract ax from each side. We're trying to isolate the y. Isolate that y. So how about if we subtract ax from each side to get closer to having y by itself? Ax minus ax is 0. This goes away. And we're left with by equals, and once again, I'm going to write that as negative ax plus c. Rather than write c minus ax, negative ax plus c. Because customarily we put that x term first before the number over here. Second step is to divide each side by b. Divide each side by b. The b's cancel, leaving us with the y by itself, which is what we wanted to do. Now break this apart into two fractions that would add to what's here, right? And the denominator of each will be b. And we will have, for that number over here, what do you get when you divide b into c? Well, c over b, right? C over b. And here in this first term, this will break apart as negative a over b times x. Negative a over b times x. Right? I know this is a little bit general. This is a lot of letters here. These letters are standing for numbers. They're really numbers. But this is what happens as you go forward in math. Things get more general and less specific. So the slope of the line, these two equations are equivalent. Everything I did here was according to our understanding of equivalent equations, doing the same thing to each side. So if we were to graph this, we can't really graph it because we don't have values for a, b, and c, but the graph of this equation would be identical to the graph of this equation. They are equivalent equations. Now, if you look down here, the slope of this line is negative a over b. Now, same thing up here. I mean, you might memorize, you don't have to, but you might memorize that, hey, when I have the equation like this, the slope of the line is going to be the opposite of a over b. That's what this work told us down here. And we got for our y-intercept c over b. C over b there. So one, I think, last thing to say. What mathematicians have done is to kind of make this easier. They'll say, all right, instead of writing y equals negative a over bx plus c over b, let's just replace the negative a over b with a letter. And the traditional letter for that is m. This m is just to make it easier. Okay? It is important to realize that when you write y equals mx, and let's say this is 3, or it's negative 2, or it's negative 2/3, or it's 4/5, whatever it might be, this m here is the same as the opposite of a over b from up here. The opposite of a over b will always be that m. That's what we just showed here. And now, as I told you before, the textbooks, this m, by the way, is traditional, goes back decades, if not centuries, using m to stand for the slope of a line. Not sure why. Might have to do with some Latin word or something like that. But the m is equivalent to the negative a over b from up here. And the part that I don't agree with in the textbooks is they would then go ahead here and write plus b. But it's not really plus b, it's really c over b. So what I'm going to do is I'm going to substitute for c over b, I'm going to substitute n. And for me, the n is the y-intercept rather than the textbooks using a b. All right, so here's the standard form up here, the standard form equation of a line. Here is the slope-intercept form, y equals mx plus n, where m is the slope, n is the y-intercept. But if you're going to ask, well, what are the m and the n in terms of the standard form, the m is negative a over b, and the n is c over b from up here. I think that's enough for now. We've gone past 25 minutes. This may seem a little bit of a reach for some of you. There is a lot of abstraction here. I'm aware of that. But you might have to come back to this. Think about reading math or watching and listening to someone explain math on YouTube like this. You don't always get it the first time. It's not like reading an easy novel where you just breeze through it, you read it for pleasure, and that's it. There are times when you're reading math in a book, you might have to spend many, many minutes on one page or even one little sentence on a page until you achieve that understanding. You may have to watch this video. I wouldn't recommend necessarily watching it today and then tomorrow, then the next day. Leave a little time. Maybe revisit this next week when we're getting into some of these topics. Go back and look at it again. And when you get more familiar with working with these things, then if you come back to this in the future, you might have a whole new appreciation for this. So keep that in mind. Stay safe, healthy, and enjoy linear equations and their graphs. So long for now.